So in this lecture, I just wanted to share a couple of sort of society relevant examples of conservation of momentum. Um, so we'll talk about rocketry again. I know we talked about it with Newton's third law, but we'll uh, go through the history a little bit more. We'll talk about Project Paperclip, Dr. Wernher von Braun. Um, so none of this will be like on a problem set or in a lab or anything. This is more of just an extra low stakes lecture that you can watch and sort of get a feel for how physics really does sort of underpin so many things in society and technologies that we rely on. So the first idea of a rocket was recorded in 400 BC by this dude here, uh, Archytas of Alexandria. And basically, he devised a way to carve this wooden pigeon, which you can see here in this picture. It's not a very good pigeon, but he basically had it steam powered. So some heated water was here in this container, and then the steam would come out the back. And using conservation momentum, Newton's third law, you would actually propel itself forward. And I believe he actually propelled it on a like a thin wire. Um, so that was sort of the first recorded evidence of someone using propulsion to move something. Uh, Hero of Alexandria also created a steam-powered engine that actually transformed heat energy or fire into motion through steam. So you can see we actually have uh, conservation or an action-reaction pair here. So the whole idea is that you've got all this steam coming out with speed and mass, which means you have to have a reaction force. So everything coming out this way, momentum wise, has to be conserved. So it's going to be canceled out. So you're going to get that thrust in this direction. And then over here's your exhaust. So that happening on both sides is how you get that conservation and actually how you get motion. So this would actually rotate. And anytime you get you put energy in and get motion out, that's essentially an engine of some sort. So the Chinese actually experimented with explosives, generally for religious purposes and religious festivals. So you think about like fireworks. So this is around 100 AD. But by the time 1200 AD rolls around, there's actually records of the Chinese using rockets actually in warfare. And you can see this picture here. This is essentially a rudimentary rocket that they can actually light and launch. If it's carefully designed, essentially the whole idea is a nice strong container on the outside. And as long as that doesn't rupture, because of conservation of momentum, all that energy has to go somewhere, all that momentum has to go somewhere, and it's going to go out the back. And that's what gives you the propellant. So moving forward, we've already talked about Tchaikovsky, but he was, yeah, and still is kind of considered the father of modern rocketry. And he was just a high school teacher, but he actually developed the rocket equation, which is this equation here. And you'll see that this actually equals a delta V, so a change in velocity. And you'll remember that the whole idea of a change in momentum is either going to be a change in mass or a change in velocity. Right? So what we're seeing is momentum sort of tied up here in this rocket equation because we have this change in velocity, and we also know we're going to have a change in momentum or velocity if we're talking about a change in momentum. So this is similar to a change in momentum. And this was in the late 1800s, early 1900s. So we can move forward to the early 1900s, 1920s, I think. Um, we have American rocket scientist Dr. Robert Goddard. And Goddard was known for, and this is Goddard, but he was known for actually achieving some insanely high altitudes with his rockets. We're talking like going up there where like weather balloons go. Um, and if you're wondering, if you grew up watching Jimmy Neutron, Jimmy Neutron's dog Goddard is actually named after Robert Goddard here. It's a fun fact. Then after Goddard, we get to Wernher von Braun. So we've been talking about the history of rockets. When we get to Wernher von Braun, an actual rocket scientist from Germany, this is where we get into Project Paperclip. So Wernher von Braun was a German rocket scientist, and he worked on army-funded liquid-propelled rockets. So you can think rocket fuel. He worked on this during the 1930s, and he also became a member of the Nazi Party in 1939. And this is von Braun here. Okay, which makes sense. He was in Germany. He was a government scientist, so his joining with the Nazi Party kind of made sense. I'm not condoning Nazis, of course, but I'm going somewhere with this. So von Braun, he was sort of the brainchild behind the V2 rocket. And here's a picture of the V2. And this rocket was pretty impressive. It actually flew, it was capable of flying more than 3,500 miles per hour, had a 200-mile range. And this was developed by von Braun and his team. But of course, as we all know, eventually Nazis surrendered after World War II. So in 1944, von Braun surrendered to the Americans. But instead of becoming like a prisoner of war, actually the US implemented Project Paperclip. And Project Paperclip was at the time sort of this undercover operation where the US brought over like 120 some German scientists, brought them to the United States and actually had them start working on US projects. So they brought von Braun and other scientists associated with the Nazi Party over to actually keep working on things. And von Braun was continued to work on rockets. Von Braun was also very much a champion of space exploration. So he wrote like lots of magazine articles and was really into wanting to get people into space. So by the time 1960 rolled around, President Eisenhower decided to take all the rocketry research and actually move it to NASA instead of it happening with the Army. It used to be Army research. Then he moved it to NASA. And during this change, von Braun actually became the director of the Marshall Space Flight Center. So not only did we have an ex-Nazi running one of our NASA centers for a while, this ex-Nazi also helped develop the Saturn V rocket engines that actually put humans on the moon. So that's a little known fact, which I think is very interesting, that we actually had help from a former Nazi getting to the moon. So that's something you can wow your family with at the dinner table sometime. So let's move on to talking about bubble chambers. So this is a little less influenced by crazy folks like Nazis. So the bubble chamber was invented by Donald Glaser in 1952, and it was basically for the purpose of detecting charged particles. So here's a picture of Glaser. And the whole idea is that the chamber is filled with superheated liquid, which interacts with charged particles as they pass through. So these charged particles will leave a trail in the liquid, and they can be photographed and studied. So from these paths, you can actually determine the particle speeds and masses, which that's interesting because that sounds a whole lot like momentum, speeds, and mass. And over here on the right, you can actually see some images of these trails, these charged particles through a bubble chamber. You can see some of these are going straight through, some of these come out in a spiral. I mean, these make really good pictures and they're very, very pretty, very interesting. But the whole idea is you can essentially, judging by how big their circles are and how big their trajectories are, their circular trajectories, you can actually determine some of these parameters. And if you know the momentum, or if you know at least something about these particles, maybe you just know the mass, or maybe you just know the velocity. If you know one thing, you can get the other. Because in this situation, we know that momentum has to be conserved. So that helps, that gives us a constraint. So we know that momentum must be conserved. Now we can move on from these little bubble chambers where we're thinking about momentum of particles and actually talk about CERN. So the European Organization for Nuclear Research, which in some other language, I can't remember what it is actually the acronym CERN. So CERN is actually home to the largest accelerator on the planet. You can see that up here in this first picture. Yeah, this you can't actually see it from the sky. This is a superimposed ring, but here's the actual particle accelerator that's in a circle, because the idea is you just keep sending particles through faster and faster, and then you send some in the opposite direction, and eventually they collide. So this ring, actually, if you look closely, there's an entire town in there. So this is the size of a whole city. This particle accelerator takes up. And if you want to look at like the inside tunnel of this particle accelerator, that's here in the second picture. So all of this here is essentially like magnets on the outside to make sure they can steer the particles, and then the particles travel through here. So this particle accelerator is responsible for some of the most high energy collisions on the planet. And when they collide two particles, usually it's protons. But the idea is they'll send a proton this way, P for proton, not momentum this time. They'll send a proton the opposite way. And when they collide here, well, these two particles explode into smaller particles. So a proton's not the smallest particle you can have. You can go subatomic, right? So the whole idea is essentially you smash these two protons together and then they fly apart into really small particles. And you'll remember from the last lecture, we talked about how explosions have conservation momentum going on. So the whole idea is that before the collision, there's some momentum. And then after the collision, same amount of momentum. So all of that initial momentum is spread between all these particles. So the idea is that if we know that momentum is conserved, well, that's going to help us identify new particles after these collisions. And you can see over here, it might be a bit grainy, but all these yellow lines, these are trails of new particles. And the idea is we can sum up all the momenta of these little particles, and that's got to be equal to the momentum we started with. So if we know the amount of momentum we're looking for, that's going to help us identify all these individual particles. So that's all I have. I just wanted to give you guys some examples. This chapter on momentum is a little short. So everything you need for homework, you've got in the first two lectures. This will be just an extra glossing over of some things that go on in society where we can actually see momentum showing up. And of course, if you're interested in any of these things, I've got plenty of links for everything throughout this entire module. So anything momentum related should be here. If you're interested, you can check that out later. And next, I think we'll move on to energy, will be the next topic that we hit.